All right, so mass fraction, and this stuff becomes kind of important because we want to know the amounts of various species in our chemical processes or metallurgical processes and stuff we're going to talk about in this class. So mass fraction bad handwriting, fraction. It's denoted in terms of xi. And so generally we write a general equation, and it is the mass of I, of your species I, over the total mass. Over the total mass. And so we can take a look at our kind of recurring theme of titanium dioxide. So let me tilt the paper a tad so you can see it a little better. So mass fraction x sub I is the mass of a species I over the total mass. And so this kind of assumes that you have species I, J, K. Okay, so if I were writing and the total mass is the mass of I plus the mass of J plus the mass of K. So I'm going to do it in a little different way than I've kind of done it before. Usually, you can say stuff like, well, let's start off with the simple one. So I have a bucket, and the bucket has 100 grams of stuff. Okay, so the stuff it has 50 grams of pebbles. It has 20 grams of glitter. And it has, let's see, we have to get to 50, so 30 grams of fairy dust. All right, so we have a bucket. It has 100 grams of stuff. Okay, so that stuff is 50 grams of pebbles, 20 grams of glitter, 30 grams of fairy dust. I'm making my troll Halloween party or something, costume, I don't know. So we want to know what the mass fraction of fairy dust is in my bucket. And it's a quite simple operation. So the x of fairy dust is 30 grams over 100 grams. You all can probably do this calculation in your head. My brain has long since reached the downhill stages. So 30 divided by 100, and I get 0.3. If you multiply that value by 100, it's 30%. So that was a little simple example. You could almost have guessed it just by looking at the numbers because I started with a nice round number of 100. But anyhow, this is how a simple example of how you would calculate mass fraction. So let's do a slightly more complex calculation for mass fraction. So let's say we'll go back to our titanium dioxide example. Let's say we have 100 grams of titanium dioxide. Okay, so we have 100 grams of titanium dioxide, and we want to know what the mass fraction of titanium is. All right, so we would do x sub Ti. So what is the mass fraction of titanium? Well, we have to do a little bit of chemistry stuff here. So if you look at the stoichiometric relationship between titanium and oxygen, in 1 mole of titanium dioxide, there are 1 mole of titanium and 2 mole of oxygen. Okay, so we want to know what the mass fraction of titanium is. So we already know what the mole fraction is. Okay, there's a 1 to 2 mole ratio there. So there's a total of 3 moles. So the mole fraction of titanium is 1 divided by 3. And maybe I will do another kind of example of that. Any other questions? So we have 100 grams of titanium dioxide. We want to know what the mass fraction of titanium is in our 100 grams of titanium dioxide. Again, to do this, we're going to have to use a little bit of chemistry. So we're going to start off. Oh, goodness gracious, the Dow leaps. That's nice. I'm getting news notifications. I'm not supposed to. Hooray. All right. We're going to start off with our 100 grams of TiO2. And I apologize for my error. And we had said earlier in the day that there are 79.866 TiO2 in 1 mole. Okay. And we said earlier that there are 1 moles of titanium, or there's 1 mole in 1 mole of TiO2. All right. And so the final thing we want, because we're trying to figure out the mass fraction of titanium, so that means we need to figure out the mass of titanium in 100 grams of TiO2. So where are you, periodic table? Here you are. Periodic table, titanium, Ti. Perdóname. Made a little mistake there. Hit my camera. And again, my camera's not the best. But here we're looking at titanium Ti. It has a atomic weight of 47.88. So we know there are 47.88 grams of titanium in 1 mole of titanium. All right, so we made this nice railroad track, and hopefully now you're getting the importance of both the railroad track method and the use of bookkeeping. So now, because we've switched species, if you've been paying attention, so we have titanium dioxide here, and we also have titanium here. So that's why this bookkeeping becomes very, very important. So we will cancel out grams of titanium dioxide. We're going to cancel out moles of titanium dioxide. And now we're left with moles of titanium and grams of titanium. Our moles of titanium will cancel out. And now we're just going to be left with grams of titanium. Okay, hopefully this makes sense. So we have 100 grams of titanium. We're going to divide it by the molecular weight, 0.866. And I'm just showing you guys the intermediary step. Hopefully you can read my fine TI calculator. I'm at 1.25 when I do that. And then you want to multiply it by 47.88 grams of titanium. And that is, I got 59.95. I'm going to go ahead and round that up to 60 just for easiness. I'm sure the more precise engineers in the world are seeing this and going, oh, that's kind of scary. Okay, so the mass of titanium is roughly, I'll just go ahead and put roughly 60 grams. Okay, so we were asked for the mass fraction of titanium, and so we know now, we started off, we were given our total grams of titanium, so that was 100 grams. 100 grams of titanium, that would be on the bottom. So it's 60 grams divided by 100 grams of titanium. So X titanium, and I apologize, I'm setting this up backwards, but if you just take a pause and take a look at it, we're figuring out the mass fraction of titanium is 60 divided by 100. Very simply, that's 0.6 or 60%. So the mass fraction of titanium and titanium dioxide is roughly 60% by our calculations. The other fraction we care about, as I said before, is mole fraction. And I kind of verbally did this. Mole fraction actually is given in terms of Yi. And why? I don't know. Haha, pun. Get it? Okay, Yi is mole fraction. And it is Ni over N total. Okay, so very, very simple. So if we want to kind of go back to what I verbally said, we want to know the mass fraction, I'm sorry, the mole fraction of titanium, or more precisely, gosh, NTI in our titanium dioxide. The amount of grams is kind of irrelevant at this point. So we know if we say we have 1 mole, that is 2 moles of oxygen and 2 moles of titanium. Okay, so the total moles in this stuff okay, so we're taking a look at titanium dioxide, okay, and we want to know the the mole fraction of titanium in titanium dioxide. So more precisely, the mole fraction of titanium, YTI. And so that equals the number of moles of titanium divided by number of moles total. So in 1 mole of titanium dioxide, you have 1 mole of titanium and 2 moles of oxygen. Okay, so that means the total number of moles is 3. So this total number of moles is 3. So the mole fraction of titanium equals 1 divided by 3, essentially. And so, yes, I'm using a calculator, which is a third. I don't know why I felt I needed the need to do that, but it's roughly 0.33 or 33%. Volumetric fraction is another thing we talk about in this class, particularly when we're dealing with exhaust gases for like furnace problems and stuff like that, which we will definitely get to. So let's think about a furnace, and we'll think about kind of the products of combustion gas. And let me think a little bit. So stuff we generally have in combustion gas, we probably get some O2, and we probably have some carbon monoxide. We probably have some carbon dioxide, and we potentially have some nitrogen. And we'll talk a little bit more about nitrogen and air. In general, in this class, we say that air is 79% nitrogen. Hopefully you can read air. And it's also 21% oxygen, but diatomic oxygen. So be careful of the diatomic nature of O2 that we have in our gases here. And hopefully you can read air. But air is generally nitrogen and oxygen in this ratio of 79 and 21%. An example of gases that we have in typical exhaust is oxygen, carbon monoxide from the combustion process, carbon dioxide from the combustion process, and then nitrogen also from air, which is generally inert, so we don't really consider it in reactions, but we have to consider it in terms of a mass balance. So let's take a quick look at an exhaust gas. Let's say we can look at it from 2 ways. So let's say we have 10 liters of oxygen, let's say 20 liters of carbon monoxide, 45 liters of carbon dioxide, and I don't know, let's do 25 liters of nitrogen, okay? And you want to get you're posed with the question, what is the volume fraction? Volume fraction, I apologize for not writing it already, is this V sub x. in the notation we use here, and is V of a species I over, you guessed it, V total. Okay, so VI, so let's say we want to know what the volume fraction of carbon dioxide is in this. So what is, gosh, I can't spell. What? Sorry. What is VCO2? All right, so VCO2. So first, we got to tabularize the total amount of liters in our exhaust gas. So we took a sampling, and this is what we got. So 10 plus 20 plus 45 plus 25. 10 plus 20 plus 45 plus 25. And that just kind of happened to equal 100. I actually strove not to. I think subconsciously I did, just to make the calculation easier. So 100 liters total. And we want to calculate our VCO2. So our VCO2, this is probably going to be way simple by this point in time, is 45 liters over 100 liters, and that equals 0.45 or 45%. Another way that we are given problems in terms of fraction, okay, is kind of doing these problems backwards, and I'll do one just for volume fraction, and the same thing kind of applies to mole fraction and mass fraction if you're given a similar problem, so kind of be aware of that. So let's take a look at our exhaust gas again, and so we have O2, and it is 16%. And we have, again, our friend carbon monoxide. I don't know if it's actually your friend. I wouldn't breathe it. We'll say it's 4.0%, so it's somewhat clean. We say we have some CO2, and that's 17%, and we can put 17.0. And so we have, again, our nitrogen, and we say our nitrogen has 63%. And so let me make sure. This kind of has to add up to 100. And that's 96.4. I made a mistake somewhere. Oh. Actually, this is 4. So yes, it adds up to 100. My bad. No, I cannot do this in my head. I'm just not that good. But anyway, let's say we have a 1 cubic meter exhaust gas. And it has this composition, okay? And we want to know what is the volume of CO2 in this. Well, let's pick another one. I think we picked CO2 that time. What is the volume of O2? So what's the volume of O2? So we have 1 cubic meter. And you can take a ratio, so you can take what's called a basis. Okay, so we're actually given 1 cubic meter. Let's change it. We can say we have 3 cubic meters of exhaust gas. Forgive me for kind of changing gears on you. So 3 cubic meters of exhaust gas. What is the volume of O2 if our composition is this? So we start off with 3 cubic meters of exhaust gas, okay? So we can imply, okay, that, all right, I had kind of a technical difficulty. Back to this gas problem. So we have 3 cubic meters of exhaust gas. We want to know what the volume of O2 is. So we start off with 3 cubic meters of gas. If you look at the relative compositions, it's 16%, 4%, 17%, and 63% for O2, CO, CO2, and N2 respectively. So we can kind of take a look at what that amount is in 1 meter cubed, or 1 cubic meter of gas. And if you look at it just kind of by inspection, you can say it has 0.16 cubic meters of O2. So we can apply that factor to this. So 3 cubic meters of gas. In 1 cubic meter of gas, there's 0.16 cubic meters of O2. Our cubic meters of gas will cancel, and we'll end up with cubic meters of O2. So 3 times 3 times 0.16 equals 0.48. All right, so we've solved for the amount of O2 in our exhaust gas.